ideas, we have predictions, but we don't honestly know. So the way we think it is that the universe is expanding. Distant galaxies are rushing away from us at immense speeds, roughly proportional to the distance. Divide the distance by the speed, you get the age of the universe. It's about 13.8 billion years. Well, what happened before that? What was it like then? Well, we think the early universe, before there were galaxies and stars and planets, was very hot and very dense. And it was a little bit lumpy, how would you know that? Well, NASA launched a satellite called the Cosmic Background Explorer satellite on this day, 32 years ago. And we measured. We saw that not only is this Big Bang story about right, but it has the primordial seeds that would grow up to become galaxies. So we know this story is probably right. So now we have movies that we can show that say what the computer thinks might have happened if this is a correct story. So that's our idea. Now we want to check it by observing everything we can. So what we think happens in the very early times, small galaxies were formed very quickly, and then the gravitational forces pulled them together and they got to collide with each other and bigger, and then the galaxies merged with each other. And as that happens, the black holes in the middle, if there are any, merge together too. That's one of our big questions. Where did the black holes come from? Then after that, the universe just continues to expand and galaxies rush apart, and we're here wondering, how did this all happen? So we want to look at those first galaxies growing. We also want to look at things nearby to us, clouds of glowing gas and dust where we know that stars are being born today. So they're beautiful to look at, and astronomers would say, well, what's inside? Well, we look at them and they're dark. They're dark areas of dust is obscuring our view of those earliest times when the stars are growing. But we can see them with infrared. Infrared light will go around the dust grains instead of bouncing off. So we can see that with the Webb telescope, and that's one of our top goals, to see how stars grow with their young planets. So that's what we're going to do. We will be looking at the solar system, too. We'll be looking, excuse me, that was the wrong word. We're going to be looking at the various instruments that excuse me, I'm going to show you the wavelength range, where we want to show how the Webb telescope fits in between the different instruments that we've had before. We saw different kinds of light waves on the picture. There are short wavelength ones and long wavelength ones. The Hubble telescope observes the light you can see, and observes ultraviolet, which will give you a sunburn, gives you a little bit of infrared, but the Webb telescope goes next. It observes wavelengths that you can see, but it goes all the way out to infrared of 28 microns wavelength, which you can't see at all. And then that complements the Spitzer Space Telescope that's been up there for a long time and has now finished its job, and it went out to even longer wavelengths. So that's what we're flying, what we're looking with. We are going to look at all the objects in the solar system. The objects in the solar system beginning with Mars and going all the way out. So we can't look any closer to the sun because the telescope would get too hot. But we can look at Mars, and it's moving, of course. We have to be able to track a moving object. We'll be looking at Mars and satellites like Europa, which orbits around Jupiter. Europa has an ocean, and it's covered with ice. And we know that because we sent a satellite to probe that one. And in between the blocks of ice, there are water jets that come out. And we're going to send a mission out there to fly through those water jets to see what's that ocean like. Maybe it has molecules in it. Maybe molecules that might be signs of life. That would be really interesting. We'll be looking at Titan. Titan is a very cold but very large satellite of Saturn. It's so cold that it's able to hold liquid oceans of methane and ethane. And it has clouds and rain and rivers and lakes. And we're sending a satellite out there with a helicopter to fly around and explore that one. So we'll be looking at all of these things way out there, everything from the most distant galaxies, the first galaxies that grew in the early universe, to everything close to home. And we'll be looking at planets around other stars. Planets around other stars, well, that's hard to see them. But once in a while, a planet will go in front of its star, and the star will blink a little bit. And you say, oh, I know there's a planet there. Our special capability here is with some of the starlight will go through the atmosphere of that planet on its way to our telescope. We can analyze that atmosphere, if there is one, and say what's in it. Molecules of various kinds, maybe especially water, which would be really interesting to see that there's a wet planet out there that might be a little bit like home. So we have altogether 4 instruments to examine all these things. There is a near-infrared camera that comes from the United States. There's a near-infrared spectrograph, which is mostly from Europe with some United States parts. There's a mid-infrared instrument, which is a partnership between Europe and the United States. And there's the far-infrared, the near-infrared imaging slitless spectrometer from Canada, along with a fine guidance sensor, which we use to make sure that we're going to get sharp pictures. All of these are complete. They're all working. They're all in the observatory ready to fly. So we're thrilled to think about what we're going to see with them.
Oh, that's wonderful, John. I know you've been with us from the mission. It's such an honor to have you here today. Thank you so much.
Thank you.
For our next guest, it's really important to remember that this mission has been an international partnership from the beginning. And so representing the European Space Agency, I'm very pleased to have with me Antonella Nota. So thank you so much for joining us, Antonella. Tell us a bit about the European Space Agency contribution to this.
Michelle, good morning. It's such a pleasure to be here. I want to tell you that at the European Space Agency, we're absolutely thrilled that we're part of this magnificent mission with our colleagues at NASA and the Canadian Space Agency. It's an international partnership that has been built over decades of work on the Hubble Space Telescope, and we are positive that there will be future collaborations in the future, because that's the only way to do big, ambitious missions like the James Webb. So the contribution that ESA provides to the Webb mission are threefold. First, the launcher, the Ariane 5 rocket, will depart from the spaceport, European spaceport in French Guiana, and will deliver this powerful telescope to L2, where it will start the journey to explore the universe. The other 2 contributions are the instruments, the near-spec instrument and the mid-infrared camera and spectrograph. Talking about the Ariane 5 for just one more second, the Ariane 5 is actually an impressive rocket, very powerful, is operational since 1996, has more than 100 successful launches, including some to L2 like Herschel and Planck. But coming back to the instruments, what kind of science will these instruments do? So before we talk about the science, I think it's important to remember that Webb will be a spectroscopic telescope more than everything. Of course, we'll take beautiful images, but spectra will be the bulk of the science. And why? Because spectra is what tells us what the objects are made of. While images, they're beautiful, they are spectacular, but they tell us the morphology, what the objects look like. But astronomers want to know the composition. So to do that, they need to split the light in its components. So spectrographs do exactly that. Like rain droplets split the sunlight in its colors when we see a rainbow after a thunderstorm. The spectrographs will produce spectacular information for astronomers to use, because while an image is worth 1,000 words, spectra for astronomers are just worth 1,000 images. What kind of objects will they look at? We're interested to know. Near-spec will observe for almost 40% of the time during the first observing cycle. And one of the things that for sure near-spec will look is the very distant universe. If you remember the Hubble Deep Field, those faint galaxies, well, near-spec will be able to take spectra of them. And because of the innovative design, we'll be able to take 100 spectra at the same time in one single exposure, extremely efficient. So we can't wait to see the first spectra for near-spec. MIRI, the mid-infrared camera and spectrograph, will look through the dust, deep into the dust, and will, for example, see the emerging stars, the baby stars. One of the key questions in astronomy is still how stars form. And MIRI will nail it, because we'll be able to observe baby stars as they emerge from their cocoon the first million years of their life. Like, for example, in a star cluster like this, NGC 602, that is full still of dust. And we know that there are thousands of baby stars there we just cannot cannot see them. And finally, I want to conclude saying that the European community is extremely engaged, committed, and ready to go. We are just waiting. If we look at the map of Europe, every single dot is an institution or a center that has played a role in Webb. And so Webb is pretty much in every single ESA member state. And we collectively will do the countdown together, and we can't wait to see the first data.
That's so exciting. Thank you so much for joining us. I'm glad to know all of our European friends are waiting for the launch too. So,
absolutely.
Yes. Well, keeping on the theme of the international collaboration for the James Webb Space Telescope, joining us right now from Montreal is Sarah Gallagher, representing the Canadian Space Agency. So, Sarah, excellent to have you here today. Tell us a bit about Canada's involvement in the Webb Telescope. Oh, there we go.
Thank you so much, Michelle. I am delighted to be here, and we are so proud to be a partner for this exciting mission. As we've heard, Canada is contributing two important elements to the Webb Telescope: the Fine Guidance Sensor and the Near Infrared Imager and Slitless Spectrograph, which we affectionately call NIRISS. And these two instruments are combined into a single structure within the telescope. These two contributions showcase our excellent industrial capacity to support space astronomy. The Fine Guidance Sensor will be used during all scientific observations made by Webb. By using the star fields to determine exactly where the telescope is looking, the system will enable the pointing that is needed to give us the exquisite images that we are so looking forward to. The Canadian astronomy community is so excited and fully engaged in the opportunity afforded by our participation in the Webb Telescope, and we have plans for lots of exciting scientific explorations. Some of the first studies will include observations of the regions around very massive stars to study how these powerhouses affect their environments. And these studies will happen really early in the observing plan with some of the early science observations. As we get closer to launch, we feel growing enthusiasm in the community for the science that is coming. The interest in our community is broad and touches on a huge variety of research topics in astronomy. This includes detailed examinations of exoplanets, the worlds around other stars, the search for the first light sources in the universe, the formation and evolution of galaxies, the life cycles of stars, and studies of small bodies such as icy moons, asteroids, and comets in our own solar system. In fact, a Canadian team will focus their studies on the atmospheres of exoplanets to determine their compositions and temperatures. Some of the research team's targets are rocky planets like the Earth. The team hopes to make the very first detection of an atmosphere on such a planet. This could give us clues as to whether or not these planets are habitable. Looking towards the far distant universe, and thus far back in time, another Canadian team will study some of the first galaxies ever formed and galaxies gathered in dense neighborhoods called clusters. They will collect images and spectra from these galaxies at different times over the history of the universe to help us better understand how galaxies evolve over time. These two programs I've just described both use the Canadian-built Webb instrument, NIRISS. We are also really pleased and so proud of the excellent scientific leadership shown by early career Canadian astronomers who are leading many of these projects during the first cycle of observations. This interest from the next generation shows the vibrancy of our community. Their work will help discover other worlds, learn more about the life cycles of stars, and paint a picture of the early universe and of galaxies as they evolve through time. We are truly looking forward to this new era in space astronomy, and we just can't wait to get started.
Thank you so much for joining us, Sarah. Great to have you. For our next guest, one of the most important places in the James Webb Space Telescope family is the Space Telescope Science Institute, and I'm joined by Klaus Pontoppidan. Welcome, Klaus.
Thank you so much, Michelle.
So tell us a bit about the involvement of STSCI and your involvement with James Webb.
Sure. So as we've heard, we're about to go on this amazing journey of discovery. And we really mean discovery, because Webb has this raw power to reveal the unexpected. We can plan what we think we're going to see, but at the end of the day, we know that nature will surprise us more often than not. So this new scientific territory, we call it Discovery Space, and Webb, being a flagship mission, is able to unravel this discovery space. So the way you do that is you have new capabilities, new technological capabilities, and Webb has that in abundance. For example, Webb will be able to see in the infrared phenomena, stars, galaxies that are 100 times fainter than what was previously possible. And so we just can't predict what's there. And we sort of know how this goes because we can look back to the Hubble Space Telescope, a previous flagship. When Hubble was launched in 1990, we had not discovered dark energy, this mysterious force that pushes the universe apart. But Hubble discovered that. We didn't know of any exoplanet in existence, but today we know thousands of exoplanets. And there are more specific discoveries as well. For example, Hubble discovered 2 new moons of Pluto that could help the New Horizons probe as it visited that world a few years ago. And we think Webb will be no different in that sense. There are almost 400 individual investigations already lined up for the first year of science with Webb, and these investigations represent thousands of scientists from all over the world. And some of those programs will address questions that we did not know we had when Webb was first designed, but it has the power to address them. For example, Webb will look at colliding neutron stars, like these cataclysmic collisions, and the debris field they create, we think now, creates some of the heavy elements in the universe, some of the heavy metals, most prominently gold, including the gold that is covering the mirrors of Webb itself. Webb will look at a lava planet where we think it might rain lava, and Webb will determine if that is really true. And finally, Webb will look at a new phenomenon that is interstellar comets. So bodies from other solar systems that at one point in the past were ejected, traveled through the universe for maybe a billion years before, for a brief moment, it zipped through our solar system. And Webb is able to quickly point at them and understand what they're made of to tell us if other solar systems are made up of the same materials as our own Earth and Sun. And so we think Webb will probably also reveal new questions for future generations of scientists to answer, some of whom may not even be born yet.
That's absolutely wonderful. Thank you so much for joining us, Klaus.
My pleasure.
All right, then. So for our last guest today, we have Amber Strawn. And Amber Strawn is the Deputy Project Scientist for Communications here at NASA Goddard Space Flight Center. And Amber, you're one of my absolute favorite storytellers, an astrophysicist. I think you see the Webb telescope as part of an incredible narrative about our place in the universe, correct?
Absolutely, yeah. I mean, my own area of research is how galaxies change over time and how they form their stars and black holes. And there's a lot about this overall process that we still just don't understand. We do know that very distant galaxies are much different than galaxies in the nearby universe that we see today, but we're sort of missing this piece of the puzzle. We haven't yet seen those very early galaxies in the early universe. And so it's like we have this 13.8 billion year story of the universe, and we're missing this sort of a few key paragraphs in the very first chapter of the story. And so what we're really trying to do here is figure out how to put all those pieces of the story together and learn more about that whole process. And of course, JWST was designed to help us find those first galaxies. And of course, galaxies are the homes of stars, and stars are the homes of planets, and planets are the cradles of life. And this telescope is definitely our next big step in our search for potentially habitable planets other than our own. So very exciting. You know, JWST in general was designed to answer some of the biggest questions that we have in astronomy today. And one of my favorite things about astronomy in general is that it really gets right down to our big questions. Where do we come from, and how do we get here, and are we alone? And these questions are more than just arcane science questions. They're questions that get to the heart of what it means to be human. And Klaus mentioned this exciting prospect of maybe we'll find things that are unexpected. And to me, that is the most exciting part of this whole mission, this idea that there are surprises out there in the universe. And I think we'll find them. It happens every single time we launch a big, bold telescope into space, and JWST is the biggest and boldest yet.
Absolutely. Thank you so much for joining us, Amber.
Sure.
We'll talk to you more later. Thank you. So before we can learn about the origin of the universe, we have to get the Webb telescope off the planet. And that's a job for a big rocket, one of the largest, the Ariane 5, and it launches from the Guyana Space Center. Located in Kourou, French Guiana, it's a tropical facility, but it's also a gateway to the stars. Few spaceports on Earth present soundscapes that include the roar of rockets, followed by the sounds of a tropical jungle once the rising spires of fire disappear above the clouds. Once Webb's Ariane 5 leaves the launch pad, flight control transfers to the Mission Operations Center in Baltimore at the Space Telescope Science Institute. It's here where mission managers will not only control the spacecraft, but also gather data from the telescope's scientific instruments. So what we're going to do now is take a quick break, and we're going to reset the stage to take live questions from the audience and also from the media. So if you'd like to join us with questions, you can go to #NASAWeb. And we'll be back in just a few minutes. We're here at the Goddard Space Flight Center. I'm Michelle Thaller. Please come and join us again.
Our universe is a wild and wonderful place. In NASA's Curious Universe podcast, NASA is your tour guide. Join astronauts, scientists, and engineers on a new adventure each episode. Investigate black holes. Spend a day on the International Space Station and meet the experts behind the revolutionary James Webb Space Telescope. Find NASA's Curious Universe in your favorite podcast app or by visiting nasa.gov/podcasts.
What's out there? Let's find out. The James Webb Space Telescope Augmented Reality app. Whoa! Check out the most extraordinary scientific instrument ever designed in your own space today, only from NASA.
Welcome back to Goddard Space Flight Center. This is the pre-launch briefing for the James Webb Space Telescope, and I'm Michelle Thaller. Now we have a panel of all of the guests that you heard from before, and they're going to tell us about the science goals of the James Webb Space Telescope, and they'll also be taking live questions from the media. So in order to get this started, I will now ask the operator, do we have questions from the media to begin with?
Yes, we do. Our first one is from Elizabeth Howell. Your line's open.
Thank you very much. This is probably for John. So among the early observations, the early release science programs, have you selected the ones yet that are going to be happening first or very quickly after first flight?
John, did you hear the question?
I think they asked what are we going to do first?
That's right, yes.
Okay, yes,
Exactly.
we have indeed
Yep.
planned the entire, let me get this off.
That's right.
We have indeed planned the entire first year of scientific observations, and we know the highest priority things. We have chosen some early release science programs that will be announced immediately after they're observed. So we'll be giving you the data as soon as we have them for those great pictures. And they cover a very wide range of topics, all the way from the solar system to the very first stars, galaxies, and black holes. Everything.
Excellent. Does that answer the question? We're all good?
It does, thank you.
Do we have any more questions from the media?
And thank you. Once again, to ask a question from the phone line, that would be star, followed by number 1. Again, that's star 1. Please unmute your line and record your name clearly as prompted. And our next question is from Stephen Clark. Your line is open.
Hi, Stephen Clark, Spaceflight Now. I just wanted to follow up on the previous question, if I could. If someone, maybe Amber or John, can talk about the plan for releasing the first images. Exactly when those will be released. Will those wait till after commissioning is over, or will the public be able to see some images? During that commissioning process, once the images are down from the observatory. And, I've seen the list of the early science programs, but what will be released first of those group of early observations, or will they be released as a group? Thank you.
Yeah, so we have a wonderful plan for these early release observations, the very first sort of beautiful science images that will be released from the telescope. And those are all taken at the very end of commissioning. So this whole commissioning process takes about 6 months. And we get the final commissioning of all 4 instruments at the very, very end of that. So we'll be taking those early release observations right at the very end, as soon as those instruments are fully commissioned, and we'll be releasing them all at that same time. So that'll be happening, about 6 months after launch.
Do we have any further questions from the media?
Yes, our next question is from Marina Korn. Your line's open.
Hi, I wondered if director's discretion at the Hubble, as I'm sure you know, is beautiful.
I'm afraid that the speaker is breaking up a little bit. I'm having trouble understanding.
Sorry.
Thank you. Please go ahead. Yes. Please go ahead.
Sorry. Yeah. Webb has any kind of direct discrepancy? Hubble Space Telescope. When Bob Williams used that, came up beautiful in the darkness. So any plans things or
Klaus, I heard you. I saw you nodding. Did you get enough of that question? I'm afraid that was a little bit broken up.
Yeah, I don't know if I didn't get the whole question, but the gist I heard was a question about whether there is this director's discretionary time, just like there's for Hubble. So just to summarize, the director's discretionary time is time that is awarded by the director of the Space Telescope Science Institute, and it's for new science that appears all of a sudden that you just must do. And if we have something like that, the community can propose for it and say, we've got to do this right now. We can't wait until the next opportunity to propose for time. And then the director can look at it and say, yes, we should absolutely do this. So yes, just the same as with Hubble, there is a director's discretionary time for Webb. So I hope that answered the question.
Do we have our next question?
Marcia Dunn, your line is open.
Good morning. This is Marcia Dunn of the Associated Press. I have seen various numbers. I'm hoping to get a consensus from the group this morning. If the universe is 13.8 billion years old, how close to the beginning is Webb actually going to see? How far back does Hubble see at its very most? And is there some other telescope or device that's even got a better record? And what will it take, if at all, to be able to look all the way back to the first moments, minutes, hours of the universe? Is that even possible? Thank you.
I think the perfect person for that is John Mather. He's been involved in many of those missions.
Yes. The first thing that we can observe directly is the cosmic microwave background radiation, which is the primordial heat of the very earliest universe. And as mentioned earlier, it has little hot and cold spots, little bumps in it, which we think eventually grow up to become stars and galaxies. The first thing you can see with a telescope is predicted to happen about 100 million years later. And so that's the objective of the Webb telescope first galaxy search. We think they're out there. We don't know exactly what they're going to be like, but we expect to see little faint, very red or very infrared dots on the picture, and then we have to analyze them to see, is that really what we hope? That says that they really are primordial, the first galaxies, the first black holes. About 100 million years.
Mm-hmm. Okay. Do we have the next question?
Irene Fox, your line's open.
Good morning. Dr. Mather, about how far out do you expect James Webb Space Telescope to be able to detect and analyze chemicals in the atmospheres of extrasolar planets? And also, do you know of any collaborative programs with gravitational wave detectors? Thank you.
I think that was addressed to me.
That's right, yes, yeah.
So, but I think other people could answer it better. At any rate, we can analyze the atmospheres of planets around other stars because of the starlight that goes through those atmospheres. And so we have a list of, I think, 65 that we're going to observe in the first year, and they're pretty close by. We're not looking way into other galaxies. We're looking as close by here because those are the easiest and best for us to study. So I think, is that the main question?
I think so. Would anybody like to add anything, Klaus?
Well, I can add, there was a question as well if there are coordination with gravitational wave detectors, and I mentioned that briefly earlier. So yes, indeed, there are programs that are set up so that when gravitational wave detectors see collisions of neutron stars, what we call kilonova, Webb will be able to relatively quickly go and look at the debris from those explosions and see what it's made of. And so, yeah, so there are several programs that are doing that already in year one.
Thank you. More questions from the media?
Yes, our next question is from Bill Harwood. Your line's open.
Thank you, Bill Harwood, CBS News. Two quick ones from me. We all see invisible light, so everybody is familiar with Hubble imagery. Can someone talk to me a little about how the images from JWST, how infrared images, will compare with that? Are they going to be as jaw-dropping as Hubble's pictures are from a public standpoint? And secondly, to follow up on Stephen Clark's earlier question, aside from the actual first science images, will we be able to follow along as you guys focus the 18 segments of the mirror? Will we be able to kind of go along with that wavefront sensing program you guys have in that, the first initial month as you're trying to get everything lined up? Thanks.
Absolutely. Amber, would you like to start?
Sure. So the question about will the images be beautiful is a great one. And the answer is absolutely yes. So this telescope is going to be 100 times more powerful than Hubble. Of course, it is an infrared telescope. And so what does infrared light look like? You can get, I always tell people when they ask this question to go and look at the infrared version of the Eagle Nebula, the Pillars of Creation. So Hubble has a little tiny bit of capability in the near infrared, and it took this stunning picture of the Eagle Nebula. So go look at that. That gives you just a little hint of how beautiful we expect these images with JWST to be. So yeah, that they will definitely be beautiful.
And as far as following on, to actually, we actually get the news coming for all the different mirror segments and the focusing, yeah?
Yes, so we definitely plan to keep the community updated on the whole commissioning process all along the way. There's lots of different ways we'll be doing that. We'll be, of course, putting out press releases for the big milestones. We'll be having, constant social media updates on our social media channels. We'll have a weekly blog. So if you go to our website, and that gets a little bit more into the technical aspects. So if you really want to learn about some of the details of what's going on in commissioning, the blog's a great place to go. So lots of different ways to keep up with what's going on during commissioning.
I know I've cleared my calendar after December 18th because we're going to be having many different briefings, many different ways that people can see what's going on and get the news out. All right, next question from the media, please.
Our next question is from John Amos. Your line's open.
Hi, thanks very much. Greetings from London, here in the UK. The Hubble Object Field took many hours to build up. I think about 8 years, something like that. How long will it take Webb to form an image 100 million years after the Big Bang? And I kind of follow up to that. Will we be able to see the black hole at that time? And if so, what kind of black hole is there be?
I know there's a number of you that can answer that question. Is somebody who'd like to go ahead?
Well,
Klaus, sure.
I can give some of it a shot here. So part of the question was how long will it take for Webb to make an extreme ultra deep field like Hubble did? So Hubble created its extreme ultra deep field. It was days and days of exposure time. Webb will do that in a couple of hours in the wavelength where there's range where there's overlap. Of course, there's this huge infrared wavelength range where Hubble could not operate, and so what we'll see there is there's no comparison. There are programs in the first year to not quite go days and days and days on end, but that will go. I think the most is 50 hours deep images. That'll be very exciting to see.
All right. Did that answer the question, or would you like a follow-up? Anything else? I think we're good?
Yeah, the black hole question.
Ah, the black hole question, that's right. Yes, that's right. So observing black holes, that's right. I know you do that, Amber, yes.
So was the question, remind me of the question.
Would you repeat the question, please?
Yeah, I mean, what kind of black hole theory may exist at that time?
In the early universe, sure. So actually one of the big puzzles that we want to solve is how the giant supermassive black holes in galaxies got so big so fast. So some of the supermassive black holes at the centers of galaxies that we see in the distant universe now are much bigger than we should expect based on our ideas of how galaxies build up over time. And so we should be able to see those supermassive black holes even further out in the more distant universe. And that will certainly help us, piece together this puzzle of how galaxies evolve over time.
Absolutely. All right, I believe we have some more questions from the media.
Our next question is Marina Corn. Your line is reopened.
Hi, Marina Corn again. Hopefully hear me better time. You said that it will indeed make use of director's discretionary, but you will do yes? And then a quick question for John. Some detail about how Webb is going to compete as a search for science like exo about its limitations given Webb is not true Earth analog.
Okay, so
capabilities like you the time background.
I think the question is about the promised limitations of finding an Earth analog, an exoplanet. Oh, sure.
Right. So, if you mean an Earth-like planet, like as in an Earth size, as a distant from the sun, and with a sun-like star, Webb is not going to characterize the atmospheres of such an object. We need the next flagship observatory to do that. What Webb will do is it will characterize the atmospheres of planets around much smaller stars than the sun. It's a little easier to do, and those can still be habitable. And I think one of the key aspects of Webb is to understand whether they indeed have at least some of the properties of habitability, but it won't be a true Earth analog.
I was actually just glancing down at some of the questions we're getting from social media, and people are asking about the TRAPPIST system. So
Yes,
does Webb have plans to observe the TRAPPIST system?
Yes, absolutely. And the TRAPPIST system is a good example of planets that orbit around a much smaller star than the sun. And so we'll get excellent data of those, and there are some that are temperate. And a big question is whether they have atmospheres.
Absolutely. Okay, I believe we have one more question. Oh, follow on, yes?
Used for.
I'm sorry, you're breaking up. Could you try to repeat that one more time?
Sorry, the discretionary time, what will it be used for?
Antonella?
So the discretionary time is used in two ways. One, as Klaus said, to do something, to follow up on the discoveries and discovery, something that cannot wait for the next time allocation. But directors in the past have also used the discretionary time to allocate it to meritorious, compelling scientific ideas. For Hubble, the Hubble Deep Field was discretionary time. So it's important to remember that there is this duality in the discretionary time, can be used for both. The community always has great input in deciding where to focus that energy and try to solve the next big question.
Oh, and thanks for adding that. The early release science program that we already talked about, that's also discretionary time.
Indeed.
Absolutely. All right, I believe there's one more question from the media.
Thank you. Marcia Dunn, your line's open.
Yes, Dr. Mather, I think, or anyone else, thank you for the 100 million earmark, but what is the current record? What is the farthest back in time scientists have seen to date with what instrument? And is it possible to ever get closer than what Webb's going to do with the 100 million earmark? Thank you.
So the Hubble Space Telescope has pushed the limit to 400,000 million years after the Big Bang. So I think there is a gap the Webb has to fill between the 400 million years and the 100 million years that John Mather was talking about. So there is an entire interval in which we have a baby universe to observe, and it will be just, Webb will just present a view that we've never seen before and will be just spectacular.
And John, to follow up, is there any way to actually look farther back than the microwave background radiation?
We can only look farther in our imagination so far. We have lots of theoretical stories that we tell and calculations we make, but there's nothing to look at directly. We have evidence of very, very, very early times that are found in the polarization of the cosmic microwave background radiation, but that's not something the Webb will address. That's for other projects, which are underway.
All right. I believe we have a question. Is the next question coming from a high schooler in New York? Yes. In social media. All right. So let's see. I'm getting a number of different social media questions. All right. So this one says, okay, what makes you think you will find habitable exoplanets this time? Are more telescopes planned? So something more about the habitable exoplanets and whether they'll follow on missions to get better observations. I think if you want to sort of revisit that, Klaus, that'd be fine.
Well, I think the question was about, what is going to come after Webb. That's what I got from, and yes, I mean there was just a process that it's called the decadal survey, where the astronomical community comes together and they think about what is the most important thing that we should do. And the highest priority of that survey was indeed we need to make a telescope after Webb, successor to Webb, that can actually observe Earth-like planets, Earth analogs around solar-type stars. It's very, very exciting, but it's in the more distant future.
Absolutely. So looking at some of the questions we're getting from social media, there are a number of them kind of along the same theme. And I think this one I'll direct to Greg, actually. This is a very big, complex mission. People are saying, are you nervous about launch? Are you excited? Tell us a bit about some of the testing and making sure this thing works and how you're feeling about all of this.
Well, I'm certainly excited. Nervous? No, I'm not. We have a really good team, technical team around the world that developed this telescope. They go through all of the best practices of building engineering units and testing those out before we build the flight units. We test at different levels as we build up to the telescope size, and we test as much as possible, as practical. We call it test as you fly. So we test it the same way it's going to operate in space and the way it's going to launch. And so we've done all of that, and I think we're in pretty good shape. I will say on launch day, I do get butterflies, pretty tough, and I always do. And I just expect that, so that doesn't surprise me anymore.
So we've talked a bit about the first galaxies and how Webb hopes to observe those. There are also some questions involving the first stars. And could the first stars be very different than the stars that we see today? Amber?
Sure, John and I are looking at each other because he's an expert in this as well. So we think that the very first stars that formed in the early universe were very, very big, very massive, much bigger than the sort of normal stars that we see in our nearby Milky Way galaxy. And they also lived out their lives extremely fast because they were only made of hydrogen and helium and none of the heavier elements that cause stars to live slower, easier lives. And so we've never observed these first population of stars. And we certainly hope we might get lucky and see those with JWST. Not sure if we will. This is one of those things about trying to find things we've never found before, is that we certainly hope to see them. Not sure if we will. But yeah, super exciting because those first stars are totally different than our sort of normal stars. I don't know if John has any more to add.
Yeah, well, one thing about them is even with the Great Webb Telescope, you can't see them individually in their normal lives. But they do two things. One is they come in herds, hundreds or thousands or millions of them together, and then you can see them, and that looks like a new galaxy. The other thing they do is they blow up when they're old, which is not very old. In fact, a few million years it takes to burn out. And then they become what we call a supernova, and it's as bright as a whole galaxy is today. So those are things we know we can see if they're out there. But they're hard to find. So that's our big challenge, is to find them and then study them in depth.
Absolutely. I believe we have another question from the media.
Thank you. Our question is from Irene Klotz. Your line's open.
Thanks, Irene Claus with Aviation Week. Mr. Robinson, could you give us please the exact date of when the fueling is scheduled to begin and how long do you think it'll last? And for anybody, could you also please provide us maybe a couple of likely astronomical targets that are likely to be among the first released images? Thanks.
I missed the very first part of the question.
I believe it had to do with, could you repeat the question? I believe it had to do with the fueling, the schedule for fueling.
Sure, just wanted to know what date is currently on the calendar to begin JWST fueling and how long it will take.
So the exact date, I don't have for you, but it will start in the next few days. Right now, hopefully before Thanksgiving. We'll see. That still keeps us on track to launch on December 18th. And as far as fueling, we just top it off like you would do in your car when you go to the gas tank. And we know we will have fueling for at least 10 years and probably much longer. Of course, we have some mandatory burns that we have to do early on after we separate from the rocket to keep us on course to L2. And we will use some burns as we need to along the way. So the fewer burns, the better for long-term life of the observatory. And so right now we're expecting many years beyond 10 years of fuel.
Thanks, Greg. I was actually referring to how long the process of fueling the telescope for launch takes. I know you said you don't have the exact date when it's going to start, but is it like a week, a couple of days, just to load JWST with its propellant?
Yeah, so fueling takes 10 days to 2 weeks from start to finish.
Thanks. And then my other question was just if someone could give us a couple of targets that might be among the first image releases. Thanks.
Who'd like to talk about first image release targets?
I think it's probably a question for Amber.
Amber?
So the first images, the first science images we expect from JWST are sort of a secret. We don't really release those to the public. We want it to be a big surprise. I don't even know what they are, so it's going to be a surprise for me too.
All right. So on social media, we seem to have some fans of Canada here, and so we're going to go back to Sarah in Montreal. So Sarah, can you tell us a little bit more about different missions that the Canadian Space Agency is collaborating with NASA on?
Yes, absolutely. So Canada has actually been collaborating with NASA from the beginning. So when Canada became the third spacefaring nation in 1962 with the Alouette space weather mission, NASA provided the launch. So the partnership goes all the way back. More recently, for space astronomy, we provided the Fine Guidance Sensor for the FUSE mission, an ultraviolet spectroscopic mission, which was actually the precursor to the Fine Guidance Sensor that was provided for the Webb Telescope. And so we partner with NASA on space astronomy, but also in other space domains. So for example, in Earth observations, space weather, and lots of other domains. And we also partner with ESA as well. So it's a long storied history. Our communities are really tight and intertwined, and we have a lot of partnerships and science projects in common. A lot of the science plans that are coming for James Webb involve international partnerships, and Canadians are active in collaborating with people from around the world. So space is truly collaborative, and as Antonella mentioned, I mean, we need to work together to achieve these big dreams. So, it's too much for any one nation. So partnership is a really important part of the endeavor.
Thank you so much, Sarah. So we've talked a lot about the first stars and the first galaxies, and there are some questions about the more close solar system observations that Webb is primed to do. I know at the opening, John, you mentioned things like Europa and Titan. The question is, can you give us some specific ideas about what they want to observe on places like Europa and Titan?
Well, sure. I don't have detail to give, but I know they're really interesting to me. So I'm just pleased that our solar system experts have chosen these targets, and basically everything you've ever heard of in the solar system, we're going to look at it. So on Europa, we want to see can we see the water jets coming out. For Titan, we want to see what's it like where we're going to land the helicopter. So everything we can get in advance of the of the encounters that we're planning to do would be good to do now. We will certainly be looking for those interstellar comets that might be coming through from other places. We don't have one in mind just yet, but we certainly expect them to come. We're getting better at finding them. So everything from the farthest out to the closest in, which is Mars.
Thank you very much. All right, I believe we have another question from the media.
Thank you. Our next question is from John Amos. Your line's open.
Thanks very much. I think this is a question for Sarah. There's a number that I've been trying to get hold of. And that is the speed at which the fine steering mirror on Webb has to move. Keep the telescope locked on its target, because I think that's controlled by the fine guidance sensor. And then I have a question about gravitational lensing. Hubble used the zoom lens effect a little further back than just its mirror instruments might have suggested it could look. So what does gravitational lensing mean for Webb?
All right, so for the first one, we'll go to Sarah to talk about the fine guidance sensor.
Sure, so I can provide some details for that. So the whole system is really complicated. So first of all, you need to have a camera that looks at the star fields, and then the system determines very precisely where the telescope is actually pointing. And so that becomes part of a feedback loop where that information is fed back into the overall system that points the telescope. There's a mirror that actually can move to keep the image steady. So you don't necessarily have to move. There's gross motions that the whole telescope does, and then there's very fine motions in order to keep it in position. And the very fine motions are actually maintained by a mirror. So, but it's just a piece of the whole system. But it takes the information from the star fields and then incorporates it in so that all the information can be put together to keep the telescope pointing precisely, so we can get those beautiful images. And I couldn't hear the second question.
Well, the second question had to do with.
No, I was just saying, do you know how fast that fine steering mirror has to move?
Sarah, did you hear the question?
No. I heard the question about the fine steering mirror. No, I don't know that offhand. We can get that information for you, but I don't know it offhand.
And then the second part of the question was about gravitational lensing and how Hubble had used it in the past, and will Webb do something similar? Who'd like to do the gravitational lensing? John?
Yeah.
Yeah, okay.
Yeah, I can say a few words. Hubble has discovered, and other telescopes have also discovered, that gravity, as Einstein said it will bend light. So that means it's like having an extra lens on the telescope way out there. So we've surveyed the whole sky, and we know where hundreds of them are, and we've chosen a list where we think that'll be the best odds to see something even farther away that's highly magnified by this extra lens in space. So we see these beautiful circles in the pictures where a distant galaxy has been magnified but distorted by an intervening gravitational field. So it's one of our most powerful techniques to see as far back as we can in time. We know where to look, and we know how to look.
Amber, would you like to add something?
Yeah, well, just one of our, one of the early release science programs, some of the very first data that will be taken by JWST in the first year deals with this exactly, is looking for these gravitational lenses in the more distant universe. And one of our scientists at Goddard, Jane Rigby, leads that program.
Absolutely. Sarah, was there something that you wanted to add at the last question?
Yeah, so one of the Canadian programs that we have is actually going to be using the nearest instrument and looking at gravitational lens systems, taking advantage of those cosmic magnifying glasses in order to look at very, very distant galaxies behind big, massive clusters, and then study their properties and just learn much more, what's the shape of them? What are they doing? Are they nice and organized? Do they have the kind of structures we see in more local galaxies? So those are the kinds of questions. So we have a program also that addresses that issue.
All right. And I believe, does that conclude our questions from the media? Do we have anything else? We have one more news question.
We have a question from Bill Harwood. Your line's open.
Hey, thanks. Hey, John, you mentioned seeing light, the very first light from clouds or big assemblies of the very first stars. Do you guys expect galaxies to exist at that point? I'm just wondering if Webb will be able to solve this chicken or the egg thing in terms of what came first.
I think you're asking about black holes coming before galaxies, or vice versa? that's
for stars.
The oldest light Webb can see
yes.
obviously comes from stars. But do you expect galaxies to have already assembled by that point, or do you expect that they're still in the process of forming as far back as Webb can see?
Well, I think we're expecting to see galaxies grow over time. They grow as gravity pulls little bits together. And the movie that we showed you has galaxies pulling together in gravity. So what we see, of course, are the stars. And as was mentioned earlier, they only last for a few million years each. So for us to see a galaxy, it has to be many, many stars so that they're all lighting up at the time that we're looking. So we certainly do expect to see the collective effect of many, many individual stars. But for us, one of the big mysteries is, do those stars make the black holes, or do the black holes make the stars? So that's the chicken and egg question we're really worried about.
Well, thank you very much. I'm afraid we'll have to wrap up the questions at this time. So that's all the time we have for this briefing, and it's been wonderful to be here with this incredible panel. There's so much more to share about this exciting mission that I really hope you'll join us at 2 o'clock Eastern Time today, because we'll be having another impressive team of engineers and mission planners to walk us through the futuristic technology that enables this golden eye that the James Webb Telescope has to strive, to seek, and to find what's out there. So thank you very much for joining us. I'm Michelle Thaller from Goddard Space Flight Center. Please join us for the 2 o'clock briefing.